So today what we're going to do is we're going to take a step-by-step how we broke confidential compute and, yes, also how we fixed it. Now, I know this is the last talk, and I know you guys want to drink your beer, go to your families, so I have a small teaser. Today we'll present 3 CVEs to you, so you have something to look forward to. And I've also added a counter, so you can check from time to time where we're at towards the CVEs. Okay? So let's start. Today on stage is me, Yair, and Ben. With me, we're both security researchers from Microsoft. And while we are the ones on stage, this is actually not just our work, but actually a lot more people. This has been a collaboration between us, many people at Microsoft, and many people at Intel. So how did we get to this collaboration? So our group is Edge and Platform Security Fundamentals. We are a defensive security group. Our role is to make sure that Microsoft products are secure as it gets. And we do that under 2 brand names. One is Morse. Morse is a walrus, for those who don't know. And that's platform security, and Sparta, which is cloud security. And as part of this, we collaborated with Intel on reviewing Intel TDX 1.5 before it is deployed in our data centers. Okay, so I've already said confidential compute and Intel TDX, and I'm sure not all of you are aware of those. So we need some background into these. So let's start with that. Okay, so in very broad strokes, this is the data center architecture. We have the hardware at the bottom, we have the hypervisor managing the VMs, and the VMs on top, which contain the customer workloads. Okay, so again, in very broad strokes, the cloud providers manage the hardware and the hypervisors, and the customers manage the VMs and run their workloads on them. Okay, this is all nice and well, but in the existing architecture, the hypervisor has full access to the VMs. Of course, we don't use it. No cloud provider actually does anything with it. But when we think about sensitive workloads and sensitive data and IPs, comes the question, what happens if I don't want to trust the infrastructure provider and I still want to run my workloads on the cloud, right? And this is becoming very significant when we think about AI. And AI models are very sensitive, high value, so we need to solve this somehow. And for that, exactly, we have confidential compute that was introduced. And the main goal of it is to remove the hypervisor from the trust of the VMs. So this can support AI use cases or regulatory use cases. And the main implementations that enable this is AMD SCV SNP and Intel TDX. And as I already said, this is the main focus of this research. Okay, so let's talk a little bit about Intel TDX architecture. So we have the old architecture, like we said, a VMM managing the legacy VMs. But now we have a new addition to it, which is the confidential world that we need to be aware of. Okay? So the VMM needs to be aware of this confidential mode. This is why we have TDX aware. The VMM is the hypervisor. And we have TDX, which is the broker for this new secure state. So Intel introduced a new CPU instruction, a SIEM call. SIEM stands for Secure Arbitration Mode. And when the VMM triggers this CPU instruction, the CPU switches to the secure state, and TDX manages the TDs, which are the confidential VMs. Now pay attention to this word TD. By the end of this talk, you'll probably be sick of it. And the way the TDs are protected is that their physical pages are encrypted, and the MMU enforces that the hypervisor doesn't have access to them. Okay? So with this architecture, the hypervisor is out of the trust boundary. Let's see what we do trust. So the TDs, of course, trust the TDX module, the CPU, obviously, some microcode, and the attestation software. What they don't trust is the BIOS, the VMM, any other software, any other devices on the platform. All of those are outside the trust boundary. okay, this sounds awesome, right? Where can I sign in? But how do I actually know as a customer that when I use the cloud and use the workloads, I am actually talking to a real confidential VM or TD? Okay, so for that, we have attestation. Okay, so the customer, the basic flow is this. The customer asks the TD, please prove that you are a valid TD, so I know this is a confidential VM. Okay, and now the TD goes to work to generate a report. It does it with the platform. So we have this struct, which is the TD report. It contains, obviously, the signature. It contains the platform measurements, as well as the TD measurements itself, which is the TD info struct. And this is how the struct looks. Now, this is the hero of this talk today. You're going to see the struct appearing many times. And it has a few interesting things in it. For example, it has the MRTD, which is the measurements of all the physical pages. So the customer can really tell that this is the exact image they bargained for and nothing else. And it contains additional things like attributes, which we'll touch on later. OK, so I finished generating the report. I send it back to the customer, who can then pass it on to an attestation server. And then if the attestation goes OK, the customer can then pass on their secrets to the TD and run their sensitive workload. So from this flow, we can see there are two ways we can attack this. One is to try and spoof the attestation, right? Convince the customer this is a valid TD, please send us your secrets. And the other one is try to target the TD right after or at some point after the secrets got there. Okay? And these were exactly the two research goals we set in mind, with the focus on TDX 1.5 new features, which were the scope of the evaluation with Intel. Now, specifically about TDX 1.0, which is the previous release, Google Project Zero have done some amazing work there as well, collaborated with Intel, and you can find their research online. Okay, so we know what we want to do. Let's start doing that. The first goal is forging attestation, and the method we're going to do it is through a new feature, which is live migration. And Ben will take it from here. Thank you.
Okay, so live migration, if you're not familiar with, it's a pretty basic capability in cloud infrastructure. Basically, it allows to migrate a VM from one physical server to another. This is routinely used in cloud infrastructure for host maintenance or load balancing. But in all cases, the hypervisor or VMM must have access into the memory and state of the VM itself in order to send it to the destination platform. Now, obviously, this is a problem for confidential compute, because we can't have the VMM access our confidential VM memory, TD, in TDX case. And even if the VMM could access the actual encrypted memory, the encrypted state of the memory, that encryption is tied to that specific TDX case, so the destination device won't be able to decrypt it. So Intel needed some new type of mechanism, a transfer mechanism, to be able to send that information to the destination device. For that reason, Intel introduced a new type of TD, of confidential VM, called service TD. As the name suggests, it's supposed to be used for servicing other main TDs. Now, service TD is a pretty general term. In principle, there's supposed to be multiple types of service TDs, but in practice, there's only one, the migration TD, which, as the name suggests, is supposed to support migration. So in this talk, you're going to hear service TD and migration TD on different contexts. In practice, they're the same thing. OK, so let's take a look at how a service TD actually works. First, the host, the VMM, needs to call the bind function in the TDX module. The module actually does the binding itself, and after that is done, the service TD can access some of the target TD metadata. TD metadata is basically a bunch of data structures used by the TDX module to manage the TD. Okay, so this binding internally is managed using a table called the binding table, which is also part of the TD metadata. And this binding table contains several properties of the bound service TD. There are two properties that we will focus on in this talk. First one is UUID, simply the unique identifier of the bound service TD. And the second one is the info hash. Info hash is the hash of the content of the TD info struct of the service TD, that same TD info struct from Attestation. So basically, the module on bind takes the TD info struct of the service TD, hash its content, and write that hash in the binding table. That way, every time the service TD later tries to access a TD metadata, the module will calculate that hash again and compares it to the one in the binding table to see if it matches. If it matches, the access is granted. Now, this binding is also reflected in the target TD's attestation, and we can see that as the self TD hash value in the same TD info struct. So basically, the module will take the same hash of the service TD's TD info struct and write it in the main TD info struct as that self TD hash, basically creating a chain of evidence of which TDs are in trust here. That way, when the main TD or target TD sends the attestation report to the server, to the attestation server of the customer, the server can validate both the main TD and any service TD that's bound to it. Let's say, for example, if we, as the untrusted host, bind some malicious service TD to a customer TD, the attestation server will be able to identify it because the self-TD hash field will have an unexpected value. OK, let's go on with the actual migration flow on TDX. So on the right side here, we've got some source platform with a TDX module and a host VMM, and on the other side, the destination platform. On the source platform, we got the client TD that we want to migrate to the destination platform, and the migration TD that's bound to it. Again, migration TD is the type of service TD. OK, so before we can actually start the migration flow, on the destination platform, the host must create a destination pair of TDs, which consists of another migration TD and a skeleton TD. Skeleton TD is basically a bare-bone TD with no actual content in it, and that host will then bind those TDs together. Now, the two migration TDs will establish a secure communication channel and authenticate each other. Now, this authentication logic is basically the responsibility of the customer to implement, but this could be done using mutual attestation or some shared customer secret. And after those migration TDs trust each other, they exchange migration session keys, which are cryptographic keys that will later be used to protect the actual client TD, the migrated TD's private data. And the next step, the two migration TDs will write those keys to their respective TD metadata, so it will be accessible to the TDX module itself. Now, on the source platform, the module will read and encrypt that TD data and metadata, everything that you want to send to the destination platform, using the session keys, of course. And the module will create out of that encrypted migration bundles. The host can then export those bundles, send them to the destination host, then the host will import those encrypted bundles, and the module will, on the destination platform, will decrypt and rebuild that client TD. Now, the client TD on the destination platform can resume execution, and the original TD on the source platform is defunct and can no longer execute. All right, that's the flow. Done. So after learning this, we pretty much asked the folks at Intel, like, OK, but who's actually responsible for validating those two migration TDs? Because, OK, they authenticate each other, but we're going to need some external entity to validate both of them, since this whole design relies on the session keys to stay secure throughout all this process. Their answer was that it is the customer responsibility to build the migration TD, to implement the authentication logic, and to later validate that those two migration TDs are actually the one in use using attestation. OK, fair enough, attestation, but that's a bit relying on the happy flow. We're still left with the question, what if the migration TD isn't trusted? So we decided to explore this scenario anyway, and this is exactly what we're going to do now. Again, let's say we've got this TDX platform, same TDX module, the same untrusted host VMM. Now, the customer requests us to spin up his TD, and let's say for a second that we actually spin up his TD. Let's call that the victim TD. Now, if we allow it to execute, and eventually it will send that attestation report, it will obviously pass because it's the valid TD. But now, when the TD will get the customer secrets, we will not have access to it. So we're not going to do that. Instead, we're going to create our own TD that is controlled by the host, and we're going to call it evil TD. Now, if that TD will send the attestation report to the attestation server, it will fail because it's evil. So we're not going to do that either. Instead, we're going to go through the migration process with a little twist. So we'll create as the host another migration TD, which is also controlled by us, by the host. We'll create a destination pair of TDs on the same platform. We don't actually need to send anything anywhere. We'll just export and import on the same platform and bind those TDs together. Now the two migration TDs will communicate and exchange keys. They don't actually care about mutual authentication at this point. The two migration TDs will write those keys to the respective TD metadata. The module will create the encrypted migration bundles, just as before. The host will export those migration bundles. So far, pretty much normal, only now, since the migration TDs are controlled by the host, they also share the session keys with the host. Now, having both the encrypted migration bundles and the session keys, the host can decrypt the bundles and manipulate them as it please. Now, we don't actually care about the memory content of that evil TD. We could always control that. What we do care about is what we couldn't control, which is the metadata, and specifically that TD infrastruct, the one that is used later for attestation. So in order to impersonate that victim TD and get the customer secrets, we're just going to use exactly the same values that that victim TD is supposed to have, so the attestation server will pass the attestation process for us. But just to focus on the more important bits, we're going to change that MRTD value, so the content of our TD will look like the same content as the victim TD, at least for the attestation server. And also, we're going to change the self-TD hash, so we eliminate the evidence of the evil migration TD that's bound to our evil TD. Instead, we'll write some expected hash of some expected migration TD that's supposed to be bound to the victim. Okay, after the manipulation, we decrypt everything back, import it on the same TDX module. The module can now, which is unaware of the tampering, simply decrypt and rebuild our evil TD. Now we've got a clone of our evil TD still controlled by the host with one small difference. It can now pass attestation and get the customer secrets.
Thank you, Ben. Now, that's awesome. But migration is a new feature. No one really uses it. Maybe I should just revert to the old TDs, right? So we really wanted to think, is there a way we can expand it also to non-migratable TDs? So let's understand how migration is determined. So again, TD infrastruct, and this time we're looking at the attributes. So bit 29 tells whether or not a TD is migratable or not. And a customer can decide that if they don't want to use the migration feature, they just set this to 0. And when we trigger the export SIEM call, then TDX module will check whether or not we can use migration and will reject the migration. And that's game over. But didn't we just say we can change the TD infrastruct during migration? Sure, we can. Of course, that would fail on the import API. Unless, of course, Intel forgot to check this on the import API. Okay, so let's see how this works right now. It is the same flow exactly as Ben described it, only now when the host manipulates the data, it would change the migratable bit to 0, it would zero out the served TD hash, and now when we build this TD, it is as if It is non-migratable TD that was never migrated and can pass attestation as any other non-migratable TD. And where we stand with, and this is actually pretty nice because this is a combination of a design issue that Ben described and a coding issue we found on top of it that expands this to all TDs. So we've met our first goal, right? Customers really can't distinguish between a good confidential VM and a compromised one that has been rooted. How did Intel fix this? Okay, so obviously they added checks on the import API. That's the first thing they did. And this was released without a CV, although I promised CVs. This was released without a CV on TDX 1.5 release, December 14th. I'll touch on the timelines later. And the second thing they did is made the serve TD hash immutable on import. So Intel maintains a file with a list of masks for the struct. When can it be changed and not? For example, import, export, debug, etc. And what they did is a relatively small change and change the import mask so this TD is now immutable. Let's understand exactly how this helps them. So if we see the main flow, like Ben described, we also added the attestation there. Now the destination TD is bound to the client TD. What this means is that if I have an evil TD as part of this flow, during the migration, I can't change the serve TD hash, and I can't eliminate the evidence of an evil serve TD in the process, and this will lead to the attestation data failing. Okay, so that was a neat fix for this. New goal, right? We achieved our first goal. The second goal is compromising a running TD. Once again, I'm handing it off to Ben, and again, we're targeting a new feature, instance binding in TDX 1.5.
Okay, so in the beginning, I described the service TD and how the module manages which service TD is bound to which TD using the binding table. So just in a short recap, the service TD tries to access some TD's metadata. The module will make sure that the hash of its TD infrastructure is the same one as in the binding table. But there's one problem with that. The TD infrastructure contains several values that could change during the lifetime of a service TD. And when that happens, the hash doesn't match anymore and the binding breaks. Now, the host can't simply bind that service TD again to that already running TD, because the DDX module only allows to bind a service TD to a target TD before the target TD is first launched. Otherwise, it won't be reflected in the attestation report that could have been already sent. So instead, what the host can do is to use instance binding in order to rebind the service TD as long as it was already bound in the past. So just to reiterate, in the normal flow, the service TD relies, or the module monarchy relies on the service TD's TD infrastructure hash to be the same as in the info hash in the binding table. But if that breaks, the host has the possibility to tell the TDX module, look, I know the hashes don't match, but if you check that UUID value instead, you'll see that it's actually the same instance of service TD, so it's fine, just fix the hash, don't worry about it. This is actually the piece of code that handles instance binding inside the bind function in the TDX module. We can see here, after that first condition of instance binding, we can see in this very long memcompare line that what the module does is simply to compare the UUID in the binding table to the actual unique identifier of the service TD, of the migration TD. If they match, so it's the same instance of service TD that was already bound, it carries on and updates the hash in the binding table to the new hash of that service TD that we are rebinding, basically fixing the hash. And this is also pretty interesting from an attacker point of view, because this means that if we want to force bind our malicious service TD to some running victim TD, all we need to have is the correct UUID value. Okay, so we've got some plan here. We take an evil migration TD and fake its UUID. We rebind that migration TD to the victim TD and take over the TD. let's see the flow. Again, TDX platform. Now we've got a victim TD that's already running its post-attestation. It's processing some customer secrets. Maybe it got some really expensive financial data that the customer wants to keep for himself, and we want to steal it. Now, there's also some migration TD that's bound to it. And now, as the host VMM, we are going to create an evil migration TD. And obviously, the UUIDs don't match. They're unique. So if the host will now try to bind that evil migration TD to the victim TD, it will fail, because normal binding won't work because the victim TD is already running, and instance binding won't work because that UUID 666 doesn't exist in the binding table. But we already know of a way to change a TD's metadata, right? It doesn't even, we don't even need to rely on attestation here. So even considering the fixes from the previous bugs, we can still do this. So we're going to do migration again. We create another migration TD, the second level migration TD, and bind it to our evil migration TD. And yes, we can chain migration TDs. We create a destination pair of TDs, just as before, export our evil migration TD, get the session keys, and edit the UUID. So after import, it's the same evil migration TD, but with the correct UUID value. OK, we're done with step number 1. Time for the rebind. This part is actually pretty straightforward. All the host needs to do is to call the bind function with instance binding enabled. And since the UUID of our evil migration TD is the same as the one in the binding table, the binding succeeds. But not only that, since the hash is actually updated to the evil migration TD that's being rebind, the original binding breaks. OK, with that migration TD out of the way, it's time for the final phase. We're going to take over that victim TD. And if you want to guess how we're going to take over the victim TD, if you don't know the answer, you haven't been paying attention. The answer is migration. We're going to create another destination pair of TDs, export the victim TD, get the session keys, and already at this point, the host can decrypt and get any secret from the victim TD. It can access any precious financial data it contains there. And not only that, we can modify anything we want before importing and creating a completely compromised TD that's still used by the client, and the client still trusts. Mission complete.
Thank you, Ben. OK, so how did Intel fix this? They disabled the feature. Turns out we don't really need instance binding right now for migration, so they just removed it till future usages. So we met our first goal, and now we've also shown that for migratable TDs, we can steal your secrets. We met both our goals, or in other words, all your TD belong to us. Let's talk about the timelines. So this is actually pretty cool. We started this research exactly 1 year ago. The kickoff meeting was May 22nd with Intel. We've done a few months of deep dives with them, and then a joint hackathon at the end of September. Intel fixed the import API issues December 14th with the 1.5.0.1.02 release. And they released the fixes for the instance binding and the migration last week with these 2 CVEs. And today we're here. So that's that. Let's talk about the summary. So actually, there is something to look forward to. We didn't cover everything we found, and the best is yet to come. We have 21 findings with 6 vulnerabilities. And some of them are still being fixed, or fixes will be issued in the coming month. And a white paper will be coming probably around August. Now, I know at this stage, it may seem like, OK, it doesn't work. But I want to say a few things about that as well. If you consider where we started with the legacy architecture, where the hypervisor is fully in the trust of the VMs, this is still a significant step forward in terms of security. And actually, even though we make it look easy, we worked really hard on finding these bugs. You can think 4 months work with multiple people. So it's very clear that TDX 1.5 was written with security in mind. And overall, some of the issues were found exactly because of some gaps in the threat model between Intel and Microsoft. And that gap is now closed. So bottom line, our confidence is actually very solid on this technology, and we support it. That's it. Let's go to happy hour.
Thank you.